Let's continue from where we stopped in our last class. In our last class, we were talking on electromagnetism, and we introduced ourselves into the right hand rule. And we remember that using the right hand rule, we have to think: are we working with a single loop of wire, or are we working with a solenoid? Is it a solenoid, or is it a single loop of wire? The way the right hand rule works for both of them are quite different. In our last class, we learned that for a single loop of wire, the current moves in the direction of thumb, the current moves in the direction of the thumb, and the magnetic field moves in the direction of the fingers. But for solenoid, the current moves with the direction of the fingers, and the magnetic field moves with the direction of the thumb. You also learned something, that the thumb always faces the north of the magnetic field. Always faces the north of the magnetic field. Are we together? Yeah. Let's continue from there today. Let's still talk more on solenoid, and let's talk about solenoid problems. Yeah. If I have a solenoid, let's say this is a solenoid. A solenoid is the coil of wire that is wound up. Let's see, a wire is wound up like a coil. Yeah, the green and yellow piece of the solenoid would that be what? Just be able. And let's say these both ends of the solenoid were connected to, let's say, light. Positive charge was connected here, and negative charge was connected here. If you remember your class on electricity, you understand that current flows from positive to negative. Therefore, current would move, watch this, up from the front, then go behind, like that, going to the negative. And if you look at it, the current is going from the front to the back, from the front to the back. And if you use your right hand rule, when does current flows from the front to the back? And in case you don't know what the front is, when you look at your fingers using your right hand rule, if you can see your fingernails, you have the back. If you can't see your fingernails, you have the front. For example, look at this image. This is the back. And this is the front, because we can't see our fingernails in this direction. I mean, not the thumb, I mean other fingers. So look at it. For this, current flows from the back to the front, from the back to the front. And when current flows from the back to the front, using your right hand rule, then the magnetic field has to be moving in this direction. Did you understand it? And if the current flows from the front to the back, look at it, from the front to the back. I hope you can see my yellow line, from the front to the back. Then the magnetic field moves in this direction. Always remember that, your right hand. If we apply this, because current will flow from positive to negative, now it's going from the front to the back. Look at it. When does current flow from the front to the back? When the magnetic field is going this way. Are we together? Therefore, for this situation, the magnetic field generated by this current would put the north here and put the south here. It's a little bit confusing, but when you look at it again, you're going to understand. Let's put an alternative scenario. Please, you'd have to bear with my again. Let's say we have an alternative scenario whereby the coil is coming from the back to the front. Yeah, let's say we have this scenario here. I'm just trying to make it thicker so you guys can see it more clearly. Yeah, let's say positive charge. This is connected to the positive side and negative side of the battery. It means current will flow from this point to this point, from A to B. Right? But now, since current is going to flow from A to B, if you look at the way current is going to flow, it's going to flow from the back to the front. Look at it, it's coming from behind to the front, from behind. That's how the current is coming from, right? And since the current is coming from behind, using your right hand rule, where would the magnetic field be facing? So let's go back to our right hand. So look at it. Now, when current comes from the back to the front, using your right hand, you don't always have to keep this image in your head. You can just hold a pen in your hand and look at your thumb. If it's from back to front, where is the magnetic field pointing to? And if it's from front to back, where is the magnetic field pointing to? Did you understand it? So if you look at your hand, or if you look at the image on the screen, you notice that for current to flow from back to the front, then the magnetic field must point in this direction. Therefore, the magnetic field generated by this current would have its north here and the south here. Why? The magnetic field lines always move out from the north. I don't know if you understand it. Is it clear? Yeah. Let's talk about something still related. Something called electromagnetic induction. What is electromagnetic induction? Yeah. This concept was first discovered by Faraday. And what did he discover? He discovered that when you move a magnet or a magnetic field, let's use the word a magnetic field, and a current carrying conductor, so if you move a magnetic field and a current carrying conductor relative to each other, what does relative to each other mean? I'll show you in a bit. Imagine this coil here. Let me try and draw the coil without the, let's say this is a coil. Let's say this is a coil of wire. Let's say this is a coil of wire. And let's say this is, let me draw a magnet battery. This out and not. Now, what did Michael Faraday discover? If I move this conductor towards this magnet, or I moved the magnet towards the conductor, or I move both of them towards each other simultaneously, he discovered that, because this is relative movement, he discovered that if one moves towards another, while the movement is going on, there is always an EMF that is induced in the current carrying conductor, inside this conductor. It's always an EMF induced in this conductor. What is EMF? For some of you that don't understand what EMF means, EMF means electromagnetic force, which is also referred to as voltage. So it means when you move a magnetic field towards a conductor or a coil or whatever it is, any conductor, or you move a conductor towards a magnetic field, or you move both of them towards each other, then there's always going to be an EMF, a voltage that's going to be induced in this coil. It means a voltage will be generated in the coil.
There's light now.
So an EMF is always induced in the coil, which means a voltage is always induced. And don't forget, when there is voltage, current will flow, which means the current will flow in the conductor. And this led us to something called Faraday's law of induction. Faraday's law of electromagnetic induction. You have to know this law, not verbatim though, you just have to understand it. Faraday's law of electromagnetic induction. And how do we put this law? What does the law state? The law states that there is always an induced EMF, or an EMF is always induced. An EMF is always induced when a conductor or a current carrying conductor moves relative to a magnetic field. Or vice versa. Now you want to put it. So when I have a conductor moving relative to a magnetic field, there's always going to be an induced EMF, an induced voltage in the current carrying conductor, or in the conductor, basically. And what this means is, when I have, like I said, I have a coil or a conductor, a loop of wire moving towards a particular magnetic field. Alright, okay. Or you have a magnetic field moving towards a conductor, there's going to be voltage. And he went further to tell us that this EMF, the induced EMF, is proportional to the change in magnetic flux. I'll explain this. I know you are beginning to see new words that you've not seen before, like magnetic flux. What is magnetic flux? Don't worry, I'll explain everything in fine detail, so you're going to understand everything. Yeah, simply put, he said that when we have this EMF induced, this EMF is directly proportional to the change in magnetic flux. I know it's beginning to look like Greek, but trust me, we'll explain everything in detail. Well, in this equation that you have here, this is a variation sign. You have, if you change this variation sign to, equality sign, then a constant is introduced, and it becomes E is equals to negative n change in phi over change in time. Please, I like writing these things in calculus wise. It becomes easier to learn and to remember. So I can say this is E is equals to negative n d phi dt. Yeah. What does this E represent? This E here represents EMF induced. That's the voltage, which is going to be measured in volts. And what does this N mean? Well, the N is the constant of proportionality. When you change variation to equality sign, a constant is introduced. So the constant of about proportionality. Well, the N represents the number of turns on the coil. Number of turns on the coil. Let's go up a little bit. Now for this coil, how many times is the coil turning? It has 1, 2, so this is a turn on the coil. 1, 2, 3, 4, 5. All these are turns on the coil. Are we together? So let's say this is a coil. It has 1 turn, 2 turns, 3 turns, 4 turns, 5 turns. So the number of turns here is 5. Are we together? So the number of the turns on the coil is the N. And what is this symbol? The something. This symbol is something that delta symbol, small letter delta, which we use in calculus to represent change. So when you see the phi, this symbol, phi, I think I need to put the symbol out separately, means magnetic flux. I'll explain what magnetic flux is in a minute. But the phi means change, because this small letter delta means change. Therefore, the phi means change in magnetic flux. And the T means change in time. So let's take it poco a poco, little by little, right? I know it's beginning to look like we are doing crazy level physics, or we are doing Greek in eating clothing of physics. But trust me, everything here is very simple if you take your time and you pay maximum attention. What is magnetic flux? But let me try and define magnetic flux for you. Magnetic flux refers to the number of magnetic field lines. So it's the amount of magnetic field lines passing through an area. And let's try and visualize what magnetic flux is. So let's try and visualize what magnetic flux means now. Now imagine I have a coil that is, or I have a single loop of wire. Now let's say I have a magnet here. The amount of magnetic field lines passing through this particular area is the magnetic flux. Now imagine I have two magnets, right? I don't even actually have to have a physical magnet. But you just need to understand that in a magnetic field, let's say this is another loop of wire. Let's say in a magnetic field, the amount of magnetic field lines that passes this area is shown below. Which of these two diagrams has more magnetic flux? It has to be this. Why? Because there are more magnetic field lines passing through this particular area, the area within the coil. Do you understand it? So that is the magnetic flux we're talking about. You could also look at it like magnetic charges. The way electricity or electric field have electric charges, magnetic field have magnetic field lines. I informally usually call it magnetic charges, but they're called magnetic lines. So you sound professional. So the amount of magnetic field lines that passes through a particular area refers to magnetic flux. Yeah, and how do we even calculate this magnetic flux? How? To calculate the magnetic flux, we need to understand that magnetic flux phi, magnetic flux is represented in phi, is equals to B multiplied by A cos theta. Are we together? And we have to start writing everything one by one. What does this B represent? The B represents the magnetic field density. How much field lines do we have in magnetic field? That's the magnetic field density. What is A? A is the area of the coil. And cos theta, theta here represents the cosine, or cos theta is the cosine of the angle. Pay attention to this very carefully. The angle between the normal to the coil. If you didn't do further maths in secondary school, don't worry, I got you covered. The normal to the coil and the magnetic field. Yeah, let's try and even visualize this. B means how many how much field lines do we have from this magnetic field? That's the magnetic field density. B is measured in Tesla. We've talked about it before. A is measured in meters. Meters squared, because area is measured in meters squared. Theta doesn't have a measurement, so it means our magnetic flux will be equals to Tesla meter squared. And 1 Tesla meter squared is known as 1 Weber. Therefore, magnetic flux is measured in Weber. You must not forget that. Weber. For those that want to write it down, it's Weber. So, the magnetic flux of the magnetic field is just the product of the magnetic field times the area of the coil times the cosine of the angle between the normal to the coil and the magnetic field. What is the normal to the coil? It's the perpendicular line to the coil. Imagine I have a coil looking like this. So this is a coil. Now, the normal to the coil is this perpendicular line to the surface of the coil. Are we together? But if we have the magnetic field passing through the coil, well, let's try and draw the magnetic field lines passing through the coil like this. Yeah. What is theta? Theta is the angle between this normal and the magnetic field. This is our theta. Are we together? So it is the angle between the magnetic field and the normal to the coil. Are we together? Let's put another diagram to see if we can illustrate it better. Let's say this is the area of the coil, and therefore this has to be the, let me even redraw the coil. Let's say this is the area of the coil. And if we accept, this has to be the normal to the coil, the perpendicular line to the coil. That's the normal. What if the magnetic field is coming or is passing through the coil this way? Sorry? So this is the direction of the magnetic field line. What is our theta? Theta is this angle here. The angle between the normal to the coil, which is this, and the magnetic field. Are we together? And what does this mean? It means because there's a direct relationship between the magnetic flux and all of these things, it means to increase my magnetic flux, if I want my magnetic flux to go higher, I can either increase my magnetic field density, like I put a stronger magnet with more field lines, or I increase the area of the coil, or I reduce the angle between the surface of the coil and the normal. Why is it reduced? There's a way cosine works. We understand that the cosine of a number increases as the number decreases. Look at it. The cosine of 0 degrees is 1, and the cosine of 90 degrees is 0. So as a number or as an angle goes closer to 0, the cosine of that angle becomes bigger. That is why you can see that cos 20 would be bigger than the cosine of an angle that is closer to 90. Let's say cos 70. You can press your calculator to validate the answer. So as an angle goes closer to 0, the cosine gets bigger. The cosine of that angle gets bigger. Why? As the angle gets closer to 90, the cosine of that angle gets smaller. So to increase cos theta, I have to decrease theta. Please, do you understand that? So I can either increase A, or increase B, or increase cos theta. And for me to increase cosine theta, theta itself has to be smaller, or it has to approach 0. Are we together? And what does this also mean? Like we said, to increase the magnetic flux, I either have to increase this, or increase this or reduce the angle or do one or more of these two things. I can do two, I can do three of them at once. I'm going to be having an increase in the magnetic flux. Now, what does this also inform us? That we have our maximum magnetic flux, or our magnetic flux is at maximum. Let me do it like this. Weber is at maximum when cosine or when theta is equals to 0. I'll show you why. Is at maximum when theta is equals to 0. This is the formula to get our maximum magnetic flux. Why do we say that? Because when BA multiplied cos 0 is 1, I'm going to be having BA. Well, our magnetic flux will be at minimum when theta is equals to 90. So our minimum magnetic flux can be calculated as BA cos 90 degrees. And let me prove this to you. Now, because cos theta that is between 0 and 90 would give me a decimal or a fraction, the fraction of BA would always be smaller than BA. I don't know if this makes sense to you. So the fraction of an apple would always be smaller than the entire apple. Does it make sense? So if we have a fraction, it reduces the entire thing to a smaller size. So when we are going to be having the maximum size, because of the cosine, the cosine should not be there, because the cosine will reduce it into a fraction. That is why the maximum magnetic flux occurs when theta is equals to 0, and the minimum occurs when theta is equals to 90. Why does the minimum occur when theta is equals to 90? You know that cos 90 is 0. Therefore, we are going to be having BA multiplied by 0. BA multiplied by 0 is going to give us what? 0. So the magnetic flux is going to be 0 Weber when theta is equals to 90. And when is theta equals to 90? When there is no angle between the normal and the magnetic field line. Let me show you. Imagine this is the area of the coil and this is the normal in white. If the magnetic field line passes exactly through the surface of the coil, what did you notice? There is no angle between the normal and the direction of the magnetic field. And therefore, theta is 0 here. This is where we are going to be having a maximum magnetic flux, because cos 0 is equals to 1. What if, okay, let me use yellow. What if we have a coil and this is the normal to the coil, but the magnetic field is passing parallel to the surface of the coil? What are we going to be having? An angle of 90. And because the magnetic field is not going through the coil, no magnetic flux is going to be induced. Are we together? Magnetic flux is going to be at the lowest, because the cosine of 90 is equals to what? 0. So if the normal and the direction of the magnetic field coincide, they are coincidental, they pass through, they are on each other, then they are going to be having the maximum magnetic flux. And if the magnetic field is perpendicular to the normal, which means if it is passing the surface of the coil, therefore there's going to be an angle 90 degrees, and they're going to be having the minimum magnetic flux induced. Are we together? Yeah. Let's even make it make sense. Let's solve a little question. Trust me, you won't be solving a lot of questions on changing magnetic flux. You just need to understand the concept and you are good. But let's just solve a question so it makes a lot of sense to you. Let's say you are told to calculate the induced EMF in a coil in the presence of in the presence of a magnetic field of intensity 0.2 Tesla, and the coil has an area of, let's say, 2 meters squared and let's say the magnetic field, watch this one, is 30 degrees to the surface of the coil. Let's say this is the question. We are told to find the induced EMF. What we are looking for is E. How do we calculate it? We know that E is equals to negative N the phi the theta. Phi means magnetic flux. So for me to be able to solve it, okay, let's say they give us the number of turns of, if they didn't give you the number of turns of the coil, assume, if you are not given the number of turns of the coil, always note that if not given M, right, assume N to be 1. Are we together? But once you are given N, you put in the value N. Are we together? So in this question, we are not giving N, so we are going to be assuming N to be 1, right? And for us to be able to even find this, we have to first find the phi. Okay, let's even say they give us time. If it moves in, let's say, 3 seconds. This you cannot assume time. You have to be given time. You cannot assume the time. We have to first find the phi dt. That's change in the magnetic flux to time. And we can do that by looking for the magnetic flux first. The magnetic flux is going to be equals to, or the phi is going to be equals to B A cos theta. So, and we know that our B is 0.2 Tesla multiplied by 2 meters squared multiplied by, well, they told us the magnetic field is 30 degrees to the surface of the coil. Let me draw this for you. Let's say this is the coil. Let's say the magnetic field is 30 degrees to the surface. And don't forget, we said theta is the angle between the magnetic field and the normal, not the surface, the normal, which is the perpendicular line. This is the normal. Therefore, if this is 30 degrees, theta is going to be equals to what? 60 degrees. Therefore, we are going to be saying multiplied by cos 60. Please, are we together? I hope you are understanding what we do. And I'm going to be having, basically, you know that cos 60 is the same thing as saying sin 30, which is equals to what? 1 over 2. So I'm going to be having 0.2 multiplied by 2 multiplied by 1 over 2, which gives me 0.2 Weber. So this is the change in the magnetic flux. Therefore, I can calculate the induced EMF to be, the number of turns wasn't given to be as unit to be 1 minus 1 into bracket 0.2 Weber divided by how many seconds? 3 seconds. And let's pull up a calculator. So we do 0.2 divided by 3 seconds. The negative is for direction, so our answer is going to be 0.066 or 0.067 volts. Don't forget, you're calculating the induced EMF, and EMF is the same thing as saying voltage. The no voltage is measured in volts. Let's just take one more question so we can grasp the concept and we can move on to the next thing. Yeah. Let's say we have another question whereby, a coil is in the presence of a magnetic field of, let's say, 4 Teslas, and it's in the there was a movement of the coil for, let's say, 12 seconds, and the magnetic field has a radius, or the coil has a radius of 3 meters, radius, please pay attention, and let's say the angle is the angle of the coil, or the angle of the magnetic field, of the magnetic field is, let's say, 40 degrees to the normal of the coil. Calculate induced EMF. Calculate the induced EMF. Now we know that the induced EMF is equals to negative N. Okay, let's even say if the number of turns is 4. If it has 4 turns, as it looks like this, 1, 2, 3, 4. Let's say this is the coil. We know that the induced EMF is equals to negative N d phi dt. But we have to first find the phi first. And we know that our d phi, or just phi, basically anything you call it, is going to be equals to B A cosine theta. We know that our B is 4 Tesla, and our area, well, they didn't give us the area, they gave us the radius. What is the area of a circle? Pi r squared. Pi times 3 squared. Are we together? So watch that. They didn't give us the area, they gave us the radius. Therefore, the area of a circle is, which is the coil, is going to be pi r squared times, what is the cosine? Our theta here is 40 degrees. Why? They said the angle of the magnetic field is 40 degrees to the normal. Let's say this is the magnetic field. The angle is 40 degrees to, not the surface right now. They said to the normal. This is the normal to the coil. This angle is 40 degrees, which is our theta basically. So we're going to be having times the cosine of 40 degrees, which takes us to, let's put the entire thing in the calculator. Let me change the calculator to a scientific calculator. So we're going to be having 4 times, open the bracket of, do we have pi on the calculator? Yes, pi times 3 squared, we have squared, times 3 squared, close bracket, times cosine, calculator is not even nice to use. So let's do little by little. Since we can't put everything in this calculator, it's a very trashy calculator. So we're going to be having cosine of 40 first. What is the cosine of 40? We have 0.76 or 0.77. And yeah, how you put it? So 0.77. And what is pi times 3 squared? Pi. Let's do it. Pi multiplied by 3 squared. We have 28.27. 28.27 times 4. And when we multiply everything together, we have 28.27 times 4 times 0.77. Our final answer is equals to 87.08. So this is our change in magnetic flux. Then we can use that to find our induced EMF, which is equals to negative N. What is our N? 4, number of turns. What is the change in magnetic flux? It's 7.08 Weber divided by, what is our change in time? 12 seconds. So we are going to be putting that into our calculator. 87.08 times 4 divided by 12. Therefore, our induced EMF is equals to 29 volts. Is that understood? And that is that under Faraday's law of electromagnetic induction. Do not forget, Faraday law told us that when we have a changing magnetic field moving towards a coil or a current carrying conductor or a conductor moving towards a changing magnetic field, or both of them are moving relative to each other, there is always an EMF induced in the conductor. Are we together? And he didn't stop there. He went on to tell us further that the EMF induced is going to be directly proportional, right, to the change in magnetic flux. Are we together? And that is Faraday's law of electromagnetic induction. It's always going to be a voltage induced in the coil. Are we together? Yeah. Let's go on and talk about something that is more detailed than Faraday's law of electromagnetic induction, which is called Lenz's law. Lenz law, or we just call it Lenz's law. What does Lenz's law tell us? Lenz's law just pushed Faraday's law of induction further. If you look at Faraday's law of induction, there was no direction. He only told us that when we have an when we have a magnetic field moving towards a conductor, or we have a conductor moving towards an EMF, towards a magnetic field. Let me say that again. So, according to Faraday, when we have a magnetic field moving towards a conductor, or a conductor moving towards a magnetic field, there is always an EMF induced, and there is no direction. It just tells us this. Now, Lenz's law went to explain this further, and Lenz's law, or Lenz law, because the lens is making us look like lenses. Right, so the Lenz's law, or Lenz law, anyhow you want to say, tell us that the EMF induced in the changing, in the conductor in the presence of a changing magnetic field. Let's just even study little by little. Let's say it in a way that everybody can understand. Yeah. So, Lenz told us that the EMF that is induced in the current carrying conductor is such that it opposes a change in the magnetic flux. So let's take it little by little. According to Faraday's law of induction, we know that an EMF is induced when a current carrying conductor moves relative to a changing magnetic field. Moves relative to a changing magnetic field. Now, Lenz's law expanded this law, which opposes a change in the magnetic flux. So, according to Lenz, or Lenz, he told us that whatever EMF is going to be induced in this coil is going to be such that he wants to do the opposite of what the magnetic flux is doing. Are we together? If the magnetic flux is passing from north to south, he wants to stop it from passing from north to south. Did you understand it? So according to Lenz's law, the EMF that is induced from Faraday's law is such that he wants to oppose that change in the magnetic flux. Let me try and visualize it for you. Let's see, I have a coil of wire. Let me draw a magnet bar. Let's say this is a magnet bar. Please forgive my drawing. So I just want you to be able to understand Lenz's law perfectly. That's why I must draw for you guys. The diagram allows you to understand perfectly, or if not perfectly, at least it increases the level of your understanding. Sorry, give me a minute. Yeah, I'll draw it perfectly back. Now let's say, see this magnet. Let's say this magnet was moving in this direction from outside, inside the coil. According to Lenz, don't forget, since the magnet is moving from, let me draw a shadow of the magnet before. Let's say this is the magnet before. Same magnet, not sound. Moving into the coil. Don't forget, the way magnets work, the magnetic flux or the magnetic field lines move out from the knot. Did you guys remember? And according to Lenz, as this is moving closer to the coil, there's going to be an EMF induced inside the coil. You have to be careful about this. It is only while this is moving, that is when an EMF is going to be induced. Let's say the magnet is just inside the coil, like this, like the diagram that we have. It's just inside the coil, it's not moving. There will be no EMF induced. Are we together? It is only when it is moving into the coil or moving out of the coil, only when it is moving relative to each other, that is when the EMF is going to be induced. Now, like I was saying, according to Lenz, if the magnet is moving inside the coil, or if the magnetic field is moving inside the coil, like we know, magnetic field lines wants to come out from the knot, or always comes out from the knot. As it's coming closer, the EMF that is induced would want to stop this magnetic flux from doing what it does. And don't forget, it stops it by generating an EMF. Always note that a voltage would always allow current to flow. So if voltage is generated, then current will be generated. And you can remember what we said in our first class. Once current flows, there's always a magnetic field around the current. Are we together? Therefore, the current from this induced EMF would want to generate, or not want to, would generate a magnetic field on its own that wants to stop what this magnetic field is doing. Are we together? Now you need to start paying attention to all these details I'm going to be saying. Like I said, if this magnetic field is trying to move into the coil, as it's trying to move or as it's moving, an EMF will be induced inside this coil that will cause current to flow, right? And this current will generate its own magnetic field that wants to oppose this magnetic field. Now let's take it one by one. The current that is going to be induced by the EMF in the coil is called eddy current. See, all these small details are what is tested in exams. So what is an eddy current? So an eddy current is the current that was induced in a coil by changing magnetic field through an induced EMF. So you have a current in a coil that was generated because an EMF was induced inside that coil. That current is called an eddy current. And what did you notice? The eddy current will always generate a magnetic field that wants to stop this original magnetic field from doing what it's doing. I don't know if it makes sense to you. I don't know if it makes sense to you. But think about it again. Why the magnetic field is trying to go into the coil, an EMF is induced, which would bring about a current. That current itself, because we know that when there is always current, there is a magnetic field. That current, or that eddy current, which is the original name, the current induced is called the eddy current, would generate its own magnetic field that wants to oppose the original magnetic field. Are we together? Because it wants to oppose the original magnetic field. I need you to understand this. If I have a knot of a magnet coming towards me, how do I stop this knot from coming towards me? I create my own magnet to stop this magnet from coming. But if I'm creating my magnet to stop this magnet from coming, is the north pole going to be here? Or is the north pole going to be here? Now you have to think about how magnet works. For magnet, like poles repel. It happens too with electricity. And unlike poles, attract. What does that mean? Negative going closer to negative would bring about a repulsion force. There will be a strong force that wants to push them away from each other. South going towards a south would bring also about this repulsion force. So north and north, south and south are like poles and they will repel. But when we have a north going towards a south or a south going towards a north, there would be an attraction force that brings them towards each other. Are we together? So how do I stop a knot from coming towards me? Well, the way this eddy current will stop it is by creating a magnetic field with a knot here. Why? Because knot would repel knot. Are you understanding it? So the current is trying to oppose the change in the magnetic field. So he doesn't want this to change. He wants to stop it. He wants to do the opposite of what the original magnetic field is doing. I don't know if you understand me. What if this magnet was coming like this? Don't worry, with enough replays, you'll understand. What if the magnet was coming like this? South, north. While he's trying to enter into the magnet, you need to understand the magnetic, as it's coming closer to the coil, or as it is moving, an EMF will be induced inside this coil. The EMF will be induced inside the coil if it moves faster. Why? Because if you go back to the formula of EMF, E is equals to N divided by T. When something moves faster, the time becomes smaller. Hope you know that. Faster movement means less time. And don't forget, when we have a smaller number at the bottom of the fraction, the result is always bigger. Are we together? But that's not the main point here. We also know that the faster it moves, the more the voltage induced inside the coil. Now let's look at this. This is moving towards the coil. An EMF is now induced inside the coil that generates an eddy current. This eddy current will create its own magnetic field that wants to stop this thing from what it's doing. Are we together? Look at it. How do you stop a south coming towards you? By generating what? A south. Did you understand it? So the eddy current will create a magnetic field with a south here to stop this south from coming. Are we together? Are we together? Very, 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 very good. So you now understand what Lenz's law is trying to say. Are we together? But this is where it becomes tough. What will be the direction of the current inside the solenoid or inside the coil? For this particular situation, a south is coming, so the eddy current would generate a south here to stop this south and keep a knot here. To know the direction of the current induced inside this coil, we have to use the right hand rule. But we would not apply the right hand rule on this magnetic field. It will be on the magnetic field generated by the eddy current. I don't know if you are understanding. It has to be the magnetic field generated by the eddy current. Now look at the magnetic field generated by the eddy current. See the north and see the south. Right? So if you are doing your right hand rule, always remember your right hand rule, your thumb must always face the north. So if I try and draw a right hand for this, with my thumb facing the north, Imagine your hand is facing like this. Imagine you are holding a pen. Imagine you are holding a pen and your thumb is facing like this. What are you going to be noticing? Current would flow from the front to the back. From the front to the back. From the front of your hand to the back. How do we know? Don't forget your fingernails is the arrow, the direction of the current. Right? And if you hold something with your nut facing this side, or your thumb facing this side with your right hand, what you will notice is you would see don't forget, I gave you an image in the beginning of this class. Where is the image? This is front, the back of your finger where you don't see your fingernails. And this is back, where you can see your fingernails. Alright? So look at it. If you hold it in this direction, with your nut going in this direction. Okay, let me use that image to explain it better for you. Look at it. If my nut, or if the solenoid generates the magnetic field with the nut facing this direction and the south facing this direction, how will current flow? Don't forget, current will flow from the front of the coil to the back of the coil. Because the way our hand is facing, see the way our hand is facing, our fingernails is facing the back. So it's going to go from the front of the coil to the back of the coil. Now let's go to those coil and see. Let's say, let's call this point A. This point. And let's call this point B. Let me even put it here. Point A. Let me put it in white. Let's call this point A. And let's call this point B. Would current flow from A to B or from B to A? I mean, inside the coil. Let's go back to our right hand rule. Our right hand rule says, the thumb would always point in the direction of the north, which is the direction of the magnetic field. Very, very, very good. So if we have our thumb facing the north, this side here, what did you notice? Current will flow from the front to the back. Current will flow from the front of the coil to the back of the coil. Look at the front of the coil here. See the front of the coil? Right? And this is behind is the back of the coil. Therefore, current will flow from A, the front of the coil, to the back. Like that. Like that. Like that. And come out at B. Therefore, current will flow from A to B. I don't know if you understand this. Let me get an animation for you. I think that would make you understand faster. You always have to look at the coil. Where is the front of the fail questions on Lenz's law? So you always have to be careful. Where is the front of the coil and where is the back of the coil? Sorry, my Chrome is trying to load. Why is trying to load? Let me try and draw another image for you. Imagine I have, a coil. Let me just do this. And use a pipe instead. Then use yellow to represent the coil. Yeah, I'm trying to draw the image. Animation is not loading very fast, or my Chrome is not loading very fast. Okay, let's say we have this point as point A, and we have this point as point B. And that's the coil. Now let's say I have a magnet. South, north. As this magnet is moving towards the coil, watch this, we'll do moving away now. As this magnet is moving towards the coil, are we together? What do we notice? Following Lenz's law, an EMF will be induced inside this coil, and this EMF will generate a current called eddy current that wants to stop this magnet from doing what it's doing. So therefore, the eddy current will create a magnetic field with a south here and a north here. Why? A south will stop a south. Does it make sense? Alright. Now, because it generates a north here and a south here, we have to use our right hand rule. Draw a right hand, or put your right hand facing this particular direction, facing the north. Hold like a pen and make sure your right hand, your thumb is facing that particular direction, the north. How would current flow? Look at it. Is it from the back to the front or from the front to the back? Current will flow from the front of the coil to the back. If you can look at your fingers, from the front of the coil. Where is the front? Let me show you the image again. Let me show you the image again with your right hand, so you can see your hand. This is the front of your finger, and this is the back. The part with fingernail is the back. The part without fingernail is the front. So, what did you notice? Current will flow from the front of the coil. Sorry. We're almost there. Current will flow from the front. If you use your right hand rule, you notice that current will flow from the front of the coil to the back. I know what you are thinking. What you are thinking is from A to B, but you'll be wrong. Why? Because this is going from the back. So this is the back of the coil. If you say from A to B, it means you are going from the back of the coil to the front, which is wrong, which is not what the right hand rule says. Right hand rule says it's going to go from the front of the coil. Look at this wire, it's going to the back. So this is the back of the coil to the front, A to B. B to A is what represents from the front of the coil, I put together, to the back. I put together from the front of the coil to the back of the coil. Front to back, front to back, front to back, front to back. Therefore, current would flow from B to A. I put together our galvanometer. Imagine we have this thing connected to a galvanometer. The galvanometer is a machine that detects the flow of current or the direction of the flow of current. Our galvanometer is going to deflect to where the current is flowing to. So our galvanometer is going to deflect towards the side from the center. I put together, it's going to deflect towards the side. I put together, because current is going from front to the back. Does this make sense? What if we have this same magnet, yeah? What if we have this same magnet moving out of the coil? Instead of moving into the coil, it is moving out of the coil. It's the south here and the north here. Same magnet moving out of the coil. Because the magnet is moving out of the coil wants to pull it back in. Are we together? It wants to do the opposite of what the original magnetic field is doing. So the coil or the eddy current in the coil will generate a magnetic field with north here. Why? Because north attracts south. So north will pull south back and south here. Are we together? Are we together? Now, if the induced current creates a magnetic field, or the eddy current creates a magnetic field with north here and south here, I need you to do your right hand rule with north facing this direction. So hold a pen with the thumb facing this north, this arrow that I'm having. Your right hand, not your left hand. Do not do the mistake. Now, what did you notice? Is current flowing from the back to the front or from the front to the back? You will notice that current is flowing from, from the back to the front. Did you understand it? It's flowing from the back to the front. Unlike before, that was flowing from the front to the back. So now the current will have to flow from the back of the coil Are we together? Let me do that in white. Current will have to flow from the back of the coil to the front, are we together, of the coil. Because our right hand rule showed us the direction. Look at your hand. Current will flow from the back of the coil to the front. Try and use your second hand as current. Look at it, flow from the back of your hand. You're going to put flow from the back of your hand to the front. So from the back of the coil, A is moving through the back of the coil and B is coming from the front of the coil. So therefore, current would flow from A to B. And therefore, if there was a galvanometer connected to this, the galvanometer would deflect right because current is moving from left to right. Let me invert the poles of the magnet. And let's try again. Let's say this is my magnet now. And the north is facing here and the south is facing here. Now the question is, if this magnet is moving towards the coil, apply Lenz's law and tell me the flow of current. If this magnet is moving towards the coil, or if this magnetic field is moving towards the coil, apply Lenz's law and tell me where current will flow, either from A to B or from B to A. Now let's analyze it. Because the north is going towards the coil, the magnetic flux, the magnetic field generated by the eddy current wants to stop this magnetic field. So therefore, it generates a knot here because he wants to stop this guy so that the knot will repel this knot. And if I have a magnetic field with the knot facing this direction, now my knot is facing this direction. Do your right hand rule with your knot facing, this arrow, my arrow direction, this direction. What would you notice? Current is flowing from the back to the front. Are we together? From the back to the front. Therefore, during this period, current will flow from A to B. Are we together? Current will flow from A to B. What about if this magnet is going out of the coil? It's no longer going in. Or this magnetic field, let's call it the magnetic field, not the magnet. Let's say the magnetic field is going out of the coil, not even into the coil anymore. So let's say the current is, let's say the magnet is moving out of the coil. Now because the magnetic field is moving out of the coil, with the knot going out, the EMF induced inside the coil will generate an eddy current that wants to stop it from moving out. Therefore, the eddy current will generate a magnetic field to pull it back. And how do you pull a knot back? By generating a south. So it generates a south here and it generates a knot here. Now do your right hand rule with the south. With your thumb, make sure your thumb is facing the knot always with your right hand rule. With your thumb facing the knot. What will be the flow of current? Will current flow from B to A or A to B? Use Lenz's law and determine. If you do your right hand rule properly, you will notice current is flowing from the front to the back. From the front to the back. So it has to go from the front of the coil, from B. Let me use red. It has to go from the front of the coil, are we together, to the back of the coil. Do you understand it? From the front of the coil, because if you use your right hand rule facing this direction, right? Facing this direction, what you're going to be noticing is current is flowing from the front of the coil to the back of the coil. So it's going to be going from B, where the coil is going from the front to the back. So one side is going to be from B to A. Does it make sense? Okay, let me try and show you with an animation and you'd probably understand better. This would increase your understanding of what we're talking about. Watch this. See the front of the coil going to the back. See the way the coil is going. Let me run this. See, as the knot is going inside the coil, as the knot is going inside the coil, what did you notice? If you apply Lenz's law, it would generate this induced current inside the coil to generate a magnetic field that wants to oppose this thing from entering inside the cylinder. So to oppose a knot, it generates a knot here. See, at this particular point, you're going to be having a knot. Now, do your right hand rule with your thumb facing downwards. Hold the pen and face downwards. What did you notice? You are noticing that current is going from the front to the back, from your right hand rule, from the front to the back. And what did you notice? Current is going from the front of the coil to the back. See, that's why your galvanometer is deflecting this side, from the front of the coil to the back, moving this way. The galvanometer will deflect in the flow of current. Does it make sense? Let's keep running it. Now look ahead. Let me run it. So look at it. As it's going into the coil, the knot is generated. Now this is where it becomes different. Snap. Sorry. Come in. I want it to go up again and I'll explain it again. Now look at it. As it's going into the coil from the knot is generated here. And if you do your right hand rule, if knot is generated facing down, current will flow from the front to the back. And that is why current is flowing from the front, see the arrow, from the front to the back. Is that clear? See, it's from the front to the back. Now this is where it becomes different. Now it is going out of the coil. Now it's no longer going into the coil. It's trying to leave the coil. And as it's trying to leave the coil, what do we notice? Don't forget, an EMF is induced that generates an eddy current inside here. And this eddy current wants to do the opposite of what this magnetic field is doing. So it generates a magnetic field with a knot here. Why is it generating a knot there? The whole goal is to pull this magnet. It wants to do the opposite of what the original magnetic field is. It doesn't want the magnetic flux to change. And as this one is trying to go, it wants to pull it back so it doesn't change. To pull this south back here, you have to generate a knot here. Are we together? And if you generate a knot here on this part of the coil, do your right hand rule facing upward. What did you notice? If you are doing your right hand rule, make sure your hand is facing your face. Put your hand in front of your face. So what did you notice? Current is flowing from the back to the front. From the back to the front. That is why you see the current going from the back of the coil to the front. Let me run it. Are you seeing it? From the back of the coil to the front. From the back of the coil to the front. Now let me change the way the coil is wounded. I've changed the way the coil is wounded now. This is the back of the coil here. Now this is the front of the coil. Let's take a quick quiz. Now this magnet wants to start coming down into the coil with the south here. How would current flow? You give me the quick guess. Forget the arrow that is on the screen. Arrow is wrong or might be correct or I don't know. But you tell me, how would currents flow? The magnet wants to go inside now. How would the current flow? Apply Lenz's law and tell me how currents will flow. You can pause this video and try to answer. Well, let's analyze it together. Because a south is coming inside the loop or inside the coil. The eddy current wants to generate a magnetic field that opposes the south. So to oppose a south, it generates a south here. And if there's a south here, there's a north here. Now, if the north is facing down, remember, according to the right hand rule, your thumb must always face the north. Therefore, your thumb must face down. Put your hand in front of your face. Put something and put your hand in front of your face. What did you notice? Current will flow from the front of the coil to the back of the coil. Guess what? This is now the front of the coil and this is the back of the coil, isn't it? So, therefore, we are going to be having currents flowing from this point to this point. The front of the coil to the back of the coil. Are we together? Are we together? Let's do this now. Why is going up? With the north pole here, because it's going into the coil, it wants to stop it from going into the coil. So the eddy current generates a magnetic field with the north here. And if the north is downward, do your right hand rule with the north downward. Current flows from the front of the coil to the back of the coil. Look at it, front of the coil to the back of the coil. What about as it's trying to leave? As it's trying to leave, the south is leaving, so he wants to pull the south back in. So to pull the south back in, you have to generate a knot. So the eddy current generates a knot here to pull this guy out. And if your knot is facing up, I mean the new knot, not this knot here, the new knot generated by the eddy current. Do your right hand rule, put your right hand in front of your face with your pen, and make sure your thumb is facing up. What did you notice? Current is flowing from the back of the coil to the front. What did you notice? From the back of the coil to the front. Is it clear? Let's change the polarity of the magnet. The same thing. You tell me, if this magnet is going downwards, how would currents flow? If you apply Lenz's law, tell me, and you must get this right this time around. Pause the video and try to figure it out. Once you are done figuring it out, you can play the video and see if you are correct. If you are done, if you apply Lenz's law, the eddy current will generate a magnetic field that wants to oppose this guy. Therefore, to oppose him not, because it's coming inside, it has to create a knot here to stop it from coming inside, to repel it. And if the knot is facing up, it's very, very easy. Current will flow from back of the coil to the front of the coil. From the back of the coil, so it's going behind, to the front of the coil. Does this make sense? And if you look at it, if you say from the back of the coil, look at it to the front of the coil, then you are correct. Now, while he's trying to go out, look at it, the south is going out of the coil. He wants to pull the south back in, so he generates a knot down. I want together to pull the south back in. And if the generated knot is facing downward, do your right hand rule for current facing downward. You see that current is flowing from the front to the back. Yeah? And if you get that, then you understand Lenz's law and Faraday's law. In our next class, we'll talk about something called the Lorentz force, and we'll practice some questions on electromagnetism before we call it a wrap. Yeah, see you in our next class. Thank you and God bless you.